All right, how was lunch? Very tasty? Yeah. Well, I get the honor of having the post-lunch sessions. Thank you very much, Masashi. The lunch coma sessions, all me. All me. Now, as your full bellies settle down into those comfy chairs, I want to encourage you to stay awake, and I'm going to use a tool I found. It's called Fear, to keep you awake. I learned this tool from my fearless leader because fear works. Fear works very well. It got him elected. Now, let's go back here. What I mean by fear is that there's going to be audience participation. If I don't get it, I'm going to pick on people. So I haven't had any shortage of that participation today. You guys have been really active, which has been great. So let's go and keep it coming, right? So I'll be talking about the drone delivery reference implementation. What's a reference implementation? Anybody? What's a reference? Don't make me define this. Come on, guys. Somebody's got to know what a reference implementation is. What is it? Come on. All right, you, sir. What do you think it is? Okay, so it's some sort of well-known sample of how you should be doing things. It's actually something that we build to try to exercise the crazy ideas that we come up with, right? Do these things hang together? I don't know. Maybe it does. It works well when we just draw it on a PowerPoint, but it may not work so well under load test. So we actually have to build it in order to test it. So that's the code that we ship is the reference implementation. Does that make sense? So that we build a lot of these reference implementations in order to prove out what we try to do, right? This is our agenda. We'll be talking about a lot of different topics. I'll go ahead and jump right in. We'll be providing some primers. Anybody have experience with Docker containers? 4, 5, 6, 7, right? How about orchestration like Kubernetes, Swarm? 1, 2, okay, 3. What about service mesh? Nobody. Service mesh? No? Anybody heard about it? No? One? Read the PDF. You're the expert. I'll be asking you. I'll be asking you. All right. So I'll go over these concepts later on. So for all the people who didn't raise their hands, I'll give you some primers and what those mean. Okay? At least what I think they mean. Let's talk about Docker's containers and Docker. Containers being small, lightweight, and portable things. Docker is the standard for containers. There are other competitors to Docker, but by far, Docker is the standard for the container format. Okay. Now, when you build a Docker image, right? You build your code, you create an image based upon that code. It's based upon a well-known base image, right? It may be ASP.NET, it could be some other base libraries. You build your code on top of that. You have your NuGet references and so forth, and you build an image. That image works the same on your laptop as it does in build and production. Let me say that again. Works exactly the same. There's no weirdness going on, right? And the same goes for on-prem and cloud. When you build it on-prem, it works great in your on-prem environment. You deploy it to a cloud environment, exactly the same. So let me tell you a story. I don't know if it's ever happened to you, but let's say I have a website and I want to use a new SDK, some new database I want to use. I want to use the latest SDK. So I install the latest SDK on my box, write the code, everything compiles, runs excellent. Check in the code. Boom, my build server dies. Why? Oh, that SDK, I gotta install it over there too, right? Okay, no problem, fix that. Build server is happy, everything goes good, we're all green. Push to production. All of a sudden I get a phone call from the CEO. Hey, the website's down, what's going on? What happened? I forgot to apply that update to production, right? This doesn't happen with containers. Everything is baked into the container. All the dependencies are baked into the image. So when you deploy it, it's got all the dependencies in it. So you don't have this crazy things where SDKs are all mismatched. Languages supported. This is a quote from Docker. I wouldn't take that verbatim as in every language, but I'd say a great many languages are supported. I don't know if I would build containers with COBOL, but that's just me. Okay, orchestration, right? So let's say that I built an image with all my code, and I deploy it into, let's say, my box or into a larger box, and it goes down. Who's going to bring it back up? Let's say I've got a bug in my code. Never happens, right? And it crashes, so it goes down. Who's going to bring it back up? Nobody. Maybe an orchestrator. That's the role of the orchestrator, the self-healing aspect. What if I, instead of running it on one container, I want to run it on n containers? That would be the scaling. Orchestration typically handles that. And basically allowing you to deploy that one container into a cluster. That's the scheduling workloads. Versioning and load balancing, those are very common features of an orchestration engine. Also the secrets and configuration management, very, very common, right? Any questions about orchestration in general? Basically the idea of having one container, I keep popping for some reason. Being able to bring it to scale without having to worry about managing each individual one, right? That's the role of the orchestrator. So as you can see here, the dev here creates the Docker image and pushes it to a central shared Docker image registry. In our case, you could use the Docker Hub or the Azure Container Registry for that purpose. That Docker image eventually will get into the your cluster, but that's really the ops part here. The ops would use the master to control the deployment into the cluster, and that would be either Kubernetes, Marathon, or Swarm are very popular ones for orchestration engines. There's also some cluster state that needs to be managed. Node state, service discovery, and leader election have to be done somehow, and that's provided by etcd, is where you'd be storing your configuration and secrets. Console and Zookeeper provides the leader election. Now, if users start making requests or hit, let's say, an endpoint on your service, that would be typically done by some sort of application gateway. And we've seen popular ones are Nginx, HA Proxy, and Azure App Gateway fill into that role. Okay. Now, when your image is deployed into your application host to actually run, that would be typically implemented by Docker Engine on VMs. Okay. All right. So let's talk about the architecturally significant requirements that we've had and see how that fits into our architecture. Well, first one is that you've got a lot of load, right? A lot of throughput we want. 10 to 100,000 requests per second on the delivery schedule. We expect a lot of load through it. We also expect that there's going to be a lot of events flying around. We need to be able to handle those large volume of events. Latency, so it needs to be quick, snappy. 99.9, so 39 uptime. So that means to me, we have to have resiliency. We can't have somebody have some services going down and somebody gives me a call on the phone, hey Francis, you got to fix that service. Oh, okay, let me fix that. Okay, you're back up. Right? None of that. It has to be automated. You're not going to have a manual process be able to achieve 3 nines or 4 nines. Okay, CI/CD, we need to be able to deploy out quickly. Let's see, recovery point, yeah, drones. Yep, last point is really, really important here, the ability to monitor. The ability to get a full picture of really everything that's going on. Do I really, is it an elephant by the tail? I need to be able to see everything that's going on. Okay? So those are the requirements that Masashi told me, Francis, this is what we got to build. Okay, wow. Let's see what that means to my architecture. So we've got requests coming in from the gateway. We need to be able to do some offloading of the authentication. The gateway doesn't want to do that, so we're going to have some sort of auth service do that. Then we're going to do some routing. We got to decide, okay, this request, should I send it to the ingestion service of the delivery scheduler? Or is it the type of thing where I can send directly to the delivery service because it's slightly different functionality, right? So let's say it goes into the ingestion service. The ingestion service is meant to handle hundreds of thousands of requests per second, high ingestion. So you may have a peak, and the expectation is that we should be able to handle the peak. The scheduler, however, handles the workflow, as Masashi's talked about before. So the workflow may operate at a much lower rate. Right? The backend services may, if you try to run at 100,000, they may just die. Right? You may need to load level there. So we have some sort of messaging going on in order to provide that difference in rate, to implement the load leveling, right? And so we've got the calls to the backend services, as Masashi mentioned, and we've got some storage for the ones that are owned by this bounded context. So the ones with the dotted dashed lines are from another bounded context, so we're not going to implement them here. Compensating transactions, that's the ability to recover from failures of the backend services. When a delivery is finished, we need to be able to remove it out of the delivery service and put it into history. And history will have everything. We want to be able to do analysis on it. We want to be able to randomly address those old deliveries, right? So let's say a delivery is finished a month ago, and I would still want to be able to say, when did it arrive, and who signed for it? You know, if you want to do some forensics, you want to be able to do that through the delivery history, right? So that's kind of the ask of management, and so we need to figure out how those constraints apply to this. So there's a lot of options. Any fans of oral hygiene? Big fan, right? So a lot of options. Even on the Microsoft stack, there's a lot of options, right? A lot of options in terms of storage, of compute. In the open source world, many more options. So let's walk you through some of the options in terms of orchestration. So Docker Swarm is a popular orchestrator, especially if you really like the Docker toolchain. It's one that is pretty popular if you're in that case. DCOS is very popular for people who are doing big data type workloads because it allows you to do both containerized workloads and non-containerized workloads. DCOS is for that. Azure Service Fabric also can host container workloads. A little bit newer to the game there. But Kubernetes has 40% market share. And it's a very, very popular one, very full-featured orchestrator. So we went with Kubernetes for the orchestration engine. Any questions there? Any pushback? Anybody agree? Pretty good choice, huh? Pretty safe, yeah? Yeah, okay. So yeah, the point is that we hired one of the lead Kubernetes developers in Microsoft. So it's an easy choice for us, but yeah, that was a pretty good choice. Right. So for storage, obviously many more storage options than this, but these are the ones that we're using in our reference implementation in various capacities. Now you can see down the bottom of the screen is the link to the AppArc guide, the Azure AppArc guide that Masashi mentioned before. That's a link to the data storage options there. That'll give you a lot more detail as to contrast and compare. So how did we choose the data? Well, this is what we ended up with, and why did we end up with that? Well, the package service is responsible for taking the detail of a delivery and putting it away. Not a lot of querying going on. Basically, I need to be able to give something to you and maybe receive it later on. I may ask you for it later on. May or may not. But I need to be able to just give you these documents pretty quickly, right? And so really that's all we're asking for it. So it was a pretty straightforward fit for the Cosmo DB. The delivery service, however, was a little bit different. Not only did we expect it to give it data, but we expected to have a lot more throughput. We need to be able to do read and writes a lot more, right? Because we're having an alternate routing over here from the gateway for people who want status. So in this scenario, we're saying status would go through the stream over here, and the new creation would go through the delivery scheduler. So delivery has different throughput requirements. Okay, it needs to be able to provide a lot more throughput, a lot faster. Now the Cosmo DB, anybody use Cosmo DB? About half the room, excellent. So, how much throughput can I put through Cosmo DB? Max, come on. Guess, let me get a guess. Come on. Sir, you raise your hand. What do you think is the max throughput through Cosmo DB? 10,000 requests per second? Was that? Request units. Oh, a request unit. Advanced user. 10,000 RUs. Any other guesses? Any higher? Here? 100,000 RUs is the max you can get. You have to have it in partition mode, the premium SKU in partition mode, so you have to basically have multiple partitions, but you can get up to 100,000 RUs. Excellent. So what's an RU? Right? Great question. What is an RU? Well, that depends. In our case, we tested Cosmo DB with a simple document. So we passed it a very small document. And just to add or create that document in Cosmo DB costs us 10 RUs. Right? So max of 100,000 RUs. Now, 10 RUs per document. Now we're looking at 10,000 documents per second. That's our max. That's for a very small document. The larger the document, the more RUs, the less throughput. So just keep in mind, that's how that works. Right? You have a max that way. So that's why it didn't seem to be a good fit for the delivery service, which needed to be able to do a lot more. Now, what I described to you was the write operation. If you want to do reads of that same document, that'll probably cost around 1 RU. Because 1 RU is supposed to be 1K of 1K transaction, but it's really 1K of read. Write could be a lot more because it's got to do some indexing. So it may be more. Now, how do you know? When you do your operation against Cosmo DB, especially if you're using the document DB client, you'll get a response back, and you can examine that response for the cost. Right? So it's valuable for you to know what's going on. You may even want to log it. Right? All right, so down here, delivery history, we're going to get a lot of data. We need to be able to run some reports on that data. Data Lake seemed to be the right fit for that. But we also needed the ability to get access to an old delivery. Now, Data Lake isn't very good for random access. If I wanted to say, give me information about delivery 123, it's got to scour a lot of data in order to find any information like that. It's not a good fit for Data Lake. Data Lake is good for lots of data, being able to do very interesting queries on lots of data. So that's why we have Cosmo DB there for the random access. Okay? All right. Service-to-service communication, my favorite topic. So there's async messaging and request-response type service-to-service communication. Let's concentrate on the async messaging. Queues versus streams, they're both async messaging type patterns. The difference between queues and streams, the way I see it, is that a queue is really meant in many ways to handle commands. You're saying, go do this, go do this, go do this. And people on the other side say, oh, I got to do this. Oh, I got to do this. Oh, I got to do that. So they actually go and do things. Streams oftentimes are used to implement a way of showing a flow of events, of things that happened. Like, oh, this happened, this happened. If you care, we'll listen to it. That's typically what it's used for. Now, can you use streams to implement workflow, like please do these things? You can, but it's not necessarily designed for everything that you get with queues, so you just have to know there's some downsides. But you can do it. Right, that makes sense? Right? All right, let's talk about Event Hubs. Event Hub, again, high throughput. Over here, we got a lot of events coming in. And Event Hub is designed for millions of events per second. Millions. So definitely our case, we want to be able to support 100,000 events coming in. This should be able to handle the ingress. Now, they end up in partitions that are then worked by consumer groups. Consumer groups are different people who care about different things. So this would be, for example, how you do your multiple subscriber. I remember that stream of data. Imagine, let's say, a deck of cards. Right? There's a stream of cards, and I care about the black cards. You may care about the red cards. You may care about all the cards. Right? We all care about different cards, and we may be looking at different parts of the stream. Right? So that would be implemented by your consumer groups. Each consumer group has to handle their own state. I have to remember at which point in the stream I read up to. You have to remember your point. You have to remember your point. So they're all different. You have to manage your own state. Okay. The event receivers. The event receivers are really meant to get data and send it off into another system. This is how you get into high throughput. Initially, we tried to implement that workflow. Remember the delivery scheduler, that workflow thing? We tried to do it in here, in the event receivers. Very, very low throughput. The event receiver is not meant to do a lot of work. It's meant to just shove the data into another system. If you try to do a lot of work here, you may not get a lot of throughput. Because you really have a limited number of partitions. By default, when you provision an event hub, you'll get 32 partitions, max. I'm not sure if you could get that up, but there's a cap. And so you're only going to get a limited number of event receivers. So again, it can work very fast as long as you're just moving moving data out of the system. Right? Yes. In a way, yes, yeah. So the event receiver will really just get some data out of a partition. It'll get that data, and then it needs to process that. Right. So it's not concerned about which partition. It just gets the data, but it has to be able to process it. Right. So the question is, how do you map the data into the partitions into event receivers? Basically, it's kind of a one-to-one. So when you send data into event hubs, you specify the partition that it goes into, and that will right. And then that will map to a specific event receiver. Now you could have more by having multiple consumer groups listen to the same stream. And for example, consumer group 1 could listen to the odd number messages and not care about the other ones. Consumer group 2 could look at the even numbers and not care about the odd number. So that's one way you could scale out, right? But the whole competing consumer is difficult here. Compared to service bus. So in this case, you've got people sending in messages into a queue, and you have receivers pulling them out of the queue. So in this case, that deck of cards, everyone's just popping them out. So you can have multiple people standing over here, popping them out as fast as I can, and the queue has the knowledge of what is left. The queue knows what has been worked. Right, so a little bit different idea. And you can have multiple receivers here implementing the competing consumer pattern. So you can have, if you want to scale out, you just add more receivers. And they would pull the content out and work them faster. Right? One thing about service bus queues and queues in general is that you have the ability to add metadata to the message. So for example, if you wanted to implement the workflow, you could have the receiver take the message and say, let me work the backend services. I'm going to call them, and let's say I finished a call to operation 1. I go ahead and update the message. Operation 2, I could update the message with that information. And if I were to die, if the receiver were to go away, then the next person that comes back would get that message and see that we've made it to stage 3. I need to continue with stage 4. So that's something that you could bake into or put back into the message. Make sense? So a little bit different, the queuing versus eventing. All right. All right, so here's our architecture again. Now here's what we did. In the middle of the delivery scheduler, we have the Azure Event Hub. So that provides the load leveling. In the case where we have errored operations that didn't complete successfully, we go ahead and put that in a queue. We don't expect a lot of them, so a queue seems to be the right fit for this. And down here for the delivery service, when we have finished deliveries, we want to go and stash them away and get it out of the delivery service. So we are using the Event Hub there. Another reason for using Event Hubs versus Service Bus, for the type of throughput we want, we're looking to do in the backend system about around 10,000 per second. That type of throughput, we did the math, would cost us something like, I think, a couple $1 million per month to run all that throughput through Service Bus. Now there is a cap on the amount of throughput you can put through Service Bus too. So it was a little challenging, but you can scale out your Service Bus, right? If one can only provide 10K per second, well, I'll do, or let's say 2K per second, I do 5 of them. Now I got 10K, right? But that type of throughput through Service Bus would cost millions of dollars per month. So the choice for the Event Hub, when we did the math on that, it was more like a couple $100 per month to handle that kind of throughput. Right? Any questions there? Okay. So the question is around the size of the messages. The Service Bus messages are considerably bigger than the Event Hub. So the question is, what if I have really big messages? How do I use Event Hub for that? Good question. We didn't run into that. Our messages are smaller, but good question. I think you may have to scale out maybe different Event Hubs, maybe partition your data. Maybe some parts of the data go into one system and another part go to another system, perhaps. So the question was, what about the pricing? Why is Event Hub so much cheaper than Service Bus? My understanding is the technology underlying is considerably different. But yeah, I don't have an answer for you in terms of why they price it the way they did. I'm just letting you know that there is a considerable price difference for the type of throughput we want to put in. Now, if you have a much smaller throughput, you may not notice. It may not be so drastic. But in this case, the requirements that I got from Masashi is build me a system that can handle 10,000 requests per second, 10,000 deliveries per second. So that's what we ended up with. Okay? All right. So gateways. What do gateways do? Well, there's aggregation. Aggregation meaning that you make a call to the gateway saying, hey, get me a product item. Well, in order to get a product item, you may want to get the product item, but you might want to get some promos, some other suggestions, and so forth. So the system may be quite complex. You may not want that complexity to be reflected in the client. You don't want the client to make 3 separate calls. You want to go and abstract that and have the gateway make those 3 calls, aggregate the result, and return that. So it looks to the client that there is one call that gave me all this data. Great. So that's aggregation. That's the aggregation pattern. Routing, in this case, we're doing the routing. In this case, we have the status calls coming through this route and the creation going through this route. So the gateway needs to be able to figure out, typically through the URL, layer 7 routing, which way to go. Okay, offloading. In this case, that's the auth service. We're offloading work. SSL termination, for example, auth service, all that type of work that we would need to do. The gateway can kind of do that so that our services don't have to worry about that. You don't want to do auth on each one of the services. We'll just go and do it in front and expect that all the authorization has been done. Otherwise, it should never even come to me. Right? Backend for front end, that's a popular pattern. If you, for example, want to provide different backends for different front ends. For example, let's say I've got a web-based client that hits this, and you've got a mobile client that hits it. maybe a desktop client that hits it. They may have different needs. They may have different caching. They may have different back-end needs. So that's something that can be done by the gateway. Throttling, as Masashi mentioned right before, at the very end of his talk, is something that gateways do very, very easily. SSL termination and security also very common asks of a gateway. So for us, we decided to go and look at these three options. There are other options, many other options, but we took a deep look at these three options. The Nginx and HA proxy are very popular reverse proxies that act as gateways. Also, Azure Application Gateway does the job too. The big difference between Nginx and HA proxy versus Application Gateway is that Application Gateway is hosted. You're giving up a little bit of control, but it's very easy to deploy. So it's your typical managed versus unmanaged. For HA proxy and Nginx, you basically have to have some knowledge of how to configure it, but you can really do what you really want to. You have much more control over Nginx and HA proxy, but you really have to know what you're doing. Make sense? All right, so here, back to our architecture. Up front is Nginx. We decided to use Nginx in that spot. Okay? Compute. We have many options for compute. So the one we're mainly focusing on is Azure Container Service with the ACS versus the AKS down here, right? But it's also called Azure Container Service. Is that confusing to you guys at all? It's very confusing to me. I was a little surprised by that. Like, why? Well, this is actually matching what Google's doing. Google has a Google Container Engine with a K in it, which is basically the Kubernetes flavor of it. We're following suit in this case. So we have the AKS, meaning the Azure Container Service. Right. The Azure Engine, or the Azure Container Service Engine, basically is allowing you to have more control. It's a XE that you run that spits out ARM templates. You can modify those ARM templates. So you can pick whatever version of Kubernetes you want, for example, and deploy that. Versus ACS right now, I think we're using 1.6 of Kubernetes that gets deployed when you ask ACS to give you a cluster. Okay. Azure Container Instances. Oh, wrong button. Azure Container Instances and Azure Functions is more in the serverless world there. So you don't have to worry about VMs. You don't have to worry about nodes. You're not paying for the month for nodes. You're paying more by execution. Azure Container Instances allows you really quick way to get one container up and running, but it doesn't really handle the whole service communication or any of those other aspects. Okay. Azure Functions, quick way to get a bit of code up and running, and you pay by execution. Right, so how do those fit in our architecture? Everything in the dotted area up here, or dashed area, Kubernetes cluster, is using ACS with the exception of the colored parts. And then you've got delivery history implemented as an Azure function. Any questions as to why we did that? No, pretty straightforward. Makes sense? Boy, I'm so good. So good at explaining this stuff. No questions. Right. Inter-service communication. Protocols. Which protocol do you like? HTTP. It's easy. A lot of tooling around it. HTTP2, a little bit less known, but more performance. gRPC, pretty popular one, but tooling is not quite as readily available. So you can need to make some choices. Also, how do you handle routing and versioning? Very important topic. Load balancing. How do you be able to spread load to a number of services or a number of service instances? How do you do that? Retry and circuit breaking, also very important topics. Right? How do you do this when you're communicating across services? Let's talk a little bit about retry. Everyone here do retry their code, right? Everybody. Anybody? Right. So retry is really for the fact that we're now running in a distributed world. We're in the cloud. And sometimes things happen that you don't expect. I want 4 examples of how you can get a transient error, something that kind of, it's a hiccup, right? 4 examples. Anybody? Sir? Network. Something in network goes down. Yeah, the router has a hiccup. Yeah, but it'll come back. So it's transient, right? Next one, number 2. What's that? A deadlock. Okay, and it could go away, right? So that's transient. Number 3. Someone in the back, come on. Yes. Database. So database is too busy, perhaps. It may come back a little bit later on when it's less busy. Yeah. Yeah. One more. Okay. Yeah. A node could go down, or that node could be garbage collecting, or whatever. Something weird with that node, right? Right. Yeah. Those are all reasons why you may want to retry, because if you call it once and it dies, what are you going to give a user like? Oh, that sucks to be you. System's down, but it's not really down. If you try it again, you may be able to give your users a much better experience if you just retry. Circuit breaking. Anybody use circuit breaking here? Come on. No? This is a very, very popular pattern. Very, very popular pattern. Anybody heard of poly or what's the Java one? Hystrix. Anybody? Poly or Java? Yeah? Okay. If you're not, you really need to be looking at these things. If you want to do retry, poly is a very, very popular way to do retry in the .NET world. Java, Hystrix came out of, I think, Netflix. That's really, really a good way to understand how to do retry. They provide a library for you to do that. But some of that retry and circuit breaking can be done for you. So you don't have to do it yourself, right? So again, we're in this microservice world. Some of the services are done .NET, some of the services are done Java, who knows? You don't have control. So maybe some people are using Poly, some people are using Hystrix, maybe some people aren't doing it at all. You don't know. So if you're putting that responsibility on the service developers, you may not have the consistency that you want, right? People may not be able to retry, and so that they may be erring out on every single transient fault, right? So the question is there a managed service that provides this out of the box? Well, I think from what you're describing through AWS, with a load balancer, with health probes, we have that. Azure load balancers provide health probes and allow you to see who's in or who's out. But if you hit the load balancer and it sends you to a VM who's having problems, and the VM responds with an error, if there's no retry, the response from the load balancer is going to be an error. So it's not, that's not retry. That's more of just spreading load, right? So we'll get into exactly how this can be implemented. But let's talk a little bit about service mesh in specific. So it didn't seem a lot of hands raised for service mesh. So let's imagine you've got your cluster and it's orchestrated by Kubernetes. So you can get your containers out there and so forth. It can do routing. Sorry. Okay. Fast forward to service mesh. Service mesh, let's go back here. Istio and Linkerd. Those are service meshes that can run on top of Kubernetes. So we look at those 2 options. We found that Istio is very new. It's just come out, I think it's on version 0.2 or something like that. We had some performance issues running at the scale that we wanted. So we ran the same test with Linkerd, and it seemed to run much faster. Istio is deployed as a sidecar. Remember, going back to what Masashi was talking about, a sidecar is that you have a pod. Basically, you have a container, and you have a pod that wraps all of the containers and all of its supporting sidecar type containers. And that pod is the smallest unit of work within an orchestrator. Okay? Pod, it's a whale thing. Pod of whales. Anyway. So they use that term, but that's what that means. It's the smallest unit of work in an orchestrator. So Istio is deployed as a sidecar. That means for every service you have, every container you have, they would deploy an Istio sidecar. And that has its own costs. Linkerd is deployed as a daemon set, so you have one per node. Okay, so it's a little bit different and different costing and performance profiles. So I'd say run it, give it a try, and see if it works for you. Linkerd is a little bit older, a little bit more established. Istio is kind of the cool new thing that's fashionable nowadays. Right, so what problem does it solve? We're talking about here. So these are the features that Service Mesh provides. Okay, let's talk about the first one, advanced routing. Okay, you do have some routing. You can route from the front end, from the gateway, but you could do some really interesting routing over here. For example, let's say you want to have some testing of your different versions, blue-green type testing. So you want to have in a production environment both your version 1 and your version 2. And let's say you want to pass a cookie and that sets, let's say I'm testing version 2. You could use Service Mesh to route all the requests to all of your version 2 nodes. That's something that's very hard to do otherwise. Also, canary testing. You can have your Service Mesh route 10% of the traffic to version 2. And if that's good, you can send 100% of the traffic. Very easy to configure with the Service Mesh. Latency-based load balancing. What in the world is that? Any guesses? Latency-based load balancing. Come on. Exactly. So if you've got one node out of 10 that's, let's say it's doing garbage collection. Okay. So it's slow. Still there, but it's slow. The Service Mesh can say, you know what, I'm not going to send as much traffic to that one. I'll send traffic to the ones that are responding faster. So a 10% drop in your functionality or in terms of your resources may not result in a 10% drop in your total performance. It could be 1%, maybe 5% drop. So that is a very popular feature for Service Mesh, is the latency-based load balancing. Right? Resiliency. So again, we mentioned retry and circuit breaking. These are not things that are easy to do. Not easy to do, right? These are things that people don't worry about. You hope that the request just goes through. It's always successful. It's just great. As we talked about, there's many ways that things can fail due to transient problems. Transient as in, it's there, but if you try again, it may go away. Another one is throttling, right? The service you're calling it too many times, so it gives you an error. But you know what? If you call it a split second later, it may go through. So that's yet another way that you would want to use retry to get around that. But again, they're hard to do consistently. So if you use a Service Mesh, if you use it properly, it will do it for you. You get it for free. Now, again, there's some costs related to having Service Mesh. There's some overhead to having Service Mesh, but that's one of the features. It will provide you the retry and circuit breaking. Also, some fault injection. You can basically test out some freaky scenarios with the Service Mesh because it operates at the service level. Protocol translation. You were talking HTTP. You wanted, but underlying, you want everything to be gRPC. That is an option with Service Meshes. Enhanced security, right? Encryption, TLS. How hard would it be to make sure that the service that I wrote talks securely to your service? Very difficult. We have to go ahead and set up our own certificates and so forth. It's not easy to do, but Service Mesh can handle it for you. Inter-service authentication. Let's say we want to make sure that only service A calls service B. Service C, not allowed. Just service A. That type of inter-service authentication, not easy to do, but you can do that pretty easily in service mesh. So did I answer your question about what the value prop? So that's really what you get with the service mesh. Monitoring. Monitoring. I'm going to assume that everyone here has systems that are amazingly monitored, right? You guys have it down. You know everything that goes on. It's perfect, right? Not my systems. Not my system. It's really, this is a hard problem, especially with the distributed world, especially with microservices. Everyone's doing their own thing. How do you get monitoring out of these things that are naturally independent? Very difficult problem. And you can get some level of monitoring through service mesh, right? Moving on. So I talked about retries. If you want to use your service mesh to retry your calls, you need to configure it. So these are the options for Linkerd. You can go to that link to look at all their response classifiers, but the first default one is non-retriable 500s. That means if I call service B, service A calls service B, and service B returns with a 500. I'm just going to say, bomber. Service mesh is going to just pass that back to me and say, sorry, it failed. No retry. Okay. Another option is to retry the read type operations. So I call service B with a get operation, or a head, or options, or trace, and it says, okay, it failed, but I'm not going to tell you. I'll just go and try it again. I'll go and retry that for you. And then there's the option of retriable idempotent 500s. I heard the conversation before. Anybody can give me a definition for idempotent? Come on. You were talking about it before. You guys know this stuff. Idempotent, come on. Yes, sir. You're a rock star, sir. You're awesome. Thank you so much for helping out. Absolutely. You can call it multiple times. You call it once, you call it 10 times. Call it 100 times. Same state. No change. So what does that mean? Put and delete operations typically, well, if you look at the REST spec, those are idempotent. What about post operations? Are those idempotent? Yeah? No? I see the heads going like this. By the way, in India, it could be the head shaking could be very. I'm going to take that as a no. But what does that mean? Well, what if I take in a delivery and I check the delivery ID, and if it's already there, I'm not going to do it. Isn't that kind of idempotent? Yeah? It's true, but post operations are not guaranteed to be. So by definition, service mesh won't know whether it is or not. Put and delete would be. So if you have something that is idempotent, make it a put or delete, or one of the read operations, and then if you configure it with service mesh will then go ahead and retry that upon error. Make sense? Yeah? Right, and all successful, basically, it'll assume errors. What errors? It's all good, right? So that's an option too, but the option we picked was a retriable idempotent 5XX. So any 500 responses that are of idempotent operations, it's going to go ahead and retry. So again, here's what inter-service communication typically looks like. Service A calls service B, B calls C, and C goes down for some strange reason, right? What'll happen? Well, the response is going to come back, hopefully maybe some sort of 500 error or so, and then service B is going to call return to service A. Now, in my experience, this response, that could come back after a long time, right? You could get a timeout. A lot of things could happen here. It could, in my wildest dreams, it would come back immediately, real fast. That's not usually the case. Typically, the requests pile up here, and maybe after a certain period of time, you start getting timeout exceptions. What's happening during that time? Whole bunch of resources are being gobbled up. Whole bunch of resources. So that's why you need some things like a circuit breaker, so you can fail fast by operations that don't inherently fail fast. Right? Anybody buying this? Yeah? Making sense? All right, so let's bring on the service mesh. So again, service A calls B, B calls C, C goes down. Service mesh will handle the retry. If it's, let's say, an idempotent or a retriable operation, it'll go ahead and do that for you. So it never even gets to B. Okay, so this just goes back to C. If it fails enough times, it'll trip it, because the service mesh knows that that was a valid response. It's not like, it's just a load balancer. It's just sending traffic. It actually knows the response. It knows the semantics of the request response. It sees that it's a failed operation, and if it sees enough of those, stop it. Stop calling service C. Let it stop being stop beating up on C. Let it recover. Send no traffic to C. Hopefully it'll come back, and then B will then just have to deal with it. It's a failure. It'll respond back to A with the failure, but it's not going to sit there and continue to pound C. It'll allow the fail fast option. And then later on, it'll send some probes to see if C is back up, and if so, it'll start sending more traffic. But that's something that circuit breaker will do for you. You don't have to implement it in all of your services. Okay? Make sense? Any questions about that? So the question is, what's the business value here? Well, the business value of the retry is that okay, so the retry is clear. Circuit breaker is you don't have to do it yourself. If you didn't do this, if you did not provide the circuit breaker at this level, what would happen is what is described before. All the requests coming in from outside will just start slamming up on C. It'd be waiting. Exactly. It'll fail fast. If this wasn't there, what would happen is that the memory consumption to handle all those incoming requests would start piling up. Your CPU, your memory, all the threads related to all those incoming requests. Nobody's going to stop those incoming requests. They're all going to come in, and all those requests are going to take up valuable resources. That will cause a cascading failure. Anybody run into cascading failures? Okay. It's a matter of time. Once you get to enough load, you will run into cascading failure. This is what happens. And if you don't really know what's going on, if you don't have good enough monitoring, it'll look like service A went down. Or maybe service B. You don't know. All we know is that the resources were down, and all of a sudden you couldn't talk to A anymore. It's not A's fault. A didn't go down, but it's unresponsive because all the system resources are depleted. Right? By putting the circuit breaker here, you fail fast. You don't get into the cascading failure. Right? Very important. Thanks for bringing it up, by the way. Yeah. I almost skipped it. Right. So cascading retries, what does that mean? Well, imagine now you've got an external dependency, and you call that external dependency through a typical client, right? If you're using CosmoDB, let's say through the DocDB client, you're using some NuGet package, and you got new document client, and you call document client, go get document. Oh, what happens if that goes down? Well, the client will retry for you. Right? You just make one call, and the client will try as many times as possible, following its retry spec. It's designed to respond to certain errors certain ways, right? It may do a fixed backoff. It may do an exponential backoff. You don't know. That's kind of part of the client. So it'll handle all the retry for you, right? Well, what if that fails? Services mesh will probably retry it for you too. Well, if this retry over here took 200 milliseconds, And then you have service mesh trying it n times. It could take a long time before this finally returns an error to service A. So what we recommend in this case, when you have external dependencies like this, is to go ahead and set a request timeout either globally or at the specific service level. You can set specific timeouts differently on different services, right? So you don't get into this crazy cascading effect with the retries. All right, that makes sense? All right, so load balancing. A lot of different options for load balancing. Azure Load Balancer. If you configure Kubernetes with a service, with a Kubernetes service, and you say to it, hey, give me a load balancer behind it, it'll set up an Azure Load Balancer. It'll actually provision an instance of the Azure Load Balancer for you. And what will it do? It'll distribute load to nodes. It knows machines, it knows VMs. So it's going to distribute load to different VMs. Whether or not the service you're looking for is on that VM or on that node. It just doesn't know. It's just going to distribute load, right? How does it evict? Well, it uses a custom probe in order to know if that node is up, right? If you've got a node that's not responding, it won't send it to that node. How does it distribute? It typically is a hash. By default, it's session affinity. So traffic from the same session will hit the same backend node. If you close, say, the browser or close that client, reopen up a new one, you get a new session, you'll go to a different backend node, right? That's kind of how it works. Kubernetes, let's say you don't define an external load balancer for it, then you're using the Kubernetes load balancer because Kubernetes knows services and pods. You're saying, I have whole set of pods over here. You know, I don't just want to have one container. I want to have 10. They all live within a pod. And I have a service that abstracts that. So I have the delivery service. And the request of the delivery service will go to my delivery service pods, right? So that type of load balancing, it provides for you. And it can do round robin or random or even IP-based affinity for that distribution. It also provides some latency-aware distribution. It's currently in alpha right now. Yeah, so I'm not sure if that's quite ready for prime time. It also has a readiness probe. I'll get into the probes in the next slide, but that allows you to evict pods from the backend pool of the Kubernetes load balancer. Okay, so you got load balancer options at different levels. And finally, you've got the load balancer option for their service mesh. Now, service mesh knows about requests as well as their failures. So it can do a lot more. One thing is it uses a circuit breaker. If enough failures to that request happen, it's just going to stop sending it to that pod. Okay? What is a pod? Great question. Mr. Actually talked a little bit about it, but basically it's the smallest unit of work within Kubernetes. Again, pod is like a pod of whales. They use a lot of the nautical terms, but it's the smallest unit of work. Basically, think of a container. You have an image. You want a container instance to do work. So let's say you create 3 of these containers. Each container will live within a pod. Now, if you want to have things that also live in that pod with your container, like sidecars, like Istio could be a sidecar or other type of sidecars, that would also live in that pod. So typically a pod would have your central container and as well as any sidecars that go with it. Okay? And then when a pod were to go down, it brings the whole pod down. And when it comes back up, it brings every container. Exactly. Yeah. Right. So the biggest feature I think here is the latency aware. Right? That's really what a lot of people use Liquid for, as well as monitoring. This is a major feature for the advanced load balancing. If you want advanced load balancing, you can get it in your service mesh, right? Self-healing. Sounds like a new age term, huh? Everyone just gets happier and your body's all heal. I wish that was the case. I'm 50 years old. I don't think there's any self-healing going on. All right, so let's talk about liveliness probes and readiness probes. These are Kubernetes concepts. Let's first talk about readiness probe. It's kind of what we talked about. It allows you to do the eviction for the Kubernetes load balancer. What you want to do is you want to provide it an end-to-end type of health check. Okay, and that's described here in the health endpoint monitoring doc that we have in the A3G. That basically allows you to hit an endpoint and get an idea. If you get like a 200 response, then end-to-end, everything's pretty good. I can talk to whatever layers I want, even talk to the database, and the health is coming back positive, so yeah, I'm ready. So the readiness probe is really, if it gives you success, then it's ready to accept traffic. If you've got a lot of init code that needs to run before you can send it traffic, then the readiness probe should fail until all that init code finishes. Okay, that's what the readiness probe does. Now let's say the readiness probe hits a backend database, which may be a good thing to do when you're doing readiness probes. The liveliness probe is different. The liveliness probe for Kubernetes is a sign for it to know when to restart the pod. Now, if the database goes down, will restarting the pod help? No, it's not. It'll just continue to restart pods all day long. So the liveliness probe is it's many ways much simpler to implement. It could just be an act back, respond with the 200. And if the stack can't even do that, you probably want to restart it. If it's deadlocked, a simple ping, a simple act back would be appropriate, right? That would be your liveliness probe as compared to your readiness probe, right? Make sense? Yeah? No questions? Right. All right, workflow. You got your Azure Logic Apps, which is a serverless managed experience. You've got Akka and Orleans are more of the actor frameworks that you could use to implement workflows. Orleans is a Microsoft product. Both the Logic Apps and Orleans are Microsoft. Akka is a very popular framework also. We decided to go with Akka, specifically the IoT Hub React extensions using Akka, because that allows you to do all the actor models in memory, and it's very, very high performant. So we went with the Akka. So here's kind of what actor systems look like. You send a message, for example, to the mailbox of the red actor. When the red actor gets around to it, it receives that message and processes it. It could send a message to the orange actor, or it could send a message to the blue actor, and around it goes. So you can see the flows in the workflow could be implemented by actors, and the actor systems are designed for high throughput. You can process a lot of content. All right, and so here you can see we implemented it in the scheduler, is using the IoT Hub React extensions. Okay. Right, so the scheduler agent supervisor pattern that Masashi talked about before, to me, it's all about resiliency. You could have many different parts of your system go down. You could have many services go down. For example, let's say the scheduler it's got a delivery request, and it starts calling the backend services. Backend services could go down. Retry. Keep trying. It can continue going down, and if it were to fail, the scheduler needs to be able to deal with that and send it to that queue. So if this goes down, we should be able to compensate for that too. So what we've done is we've decided that all the backend systems, all the calls need to be idempotent. Because I need to be able to call you multiple times. If this were to go down, something else is going to come back, take that message out of the queue or the stream, and call you with it. So it needs to be, all these backend services need to be idempotent. So this is how we achieve the resiliency around that. Okay. The whole idea here is that things will fail, but you need need to be able to handle it as gracefully as possible. Okay, so let me go to my demo. All right, so I've talked about containers and all that. Well, what does that mean? You've done a lot of hand waving. How do I do this? Well, let's do Visual Studio, file, new project. I'll go ahead and create an ASP.NET Core project, web application in this case. And it's going to give me the option of enable Docker support. What does that mean? That's a new button. What in the world is that? Well, if I don't check that, then it's the old-fashioned, not old-fashioned, it's the traditional experience. You're dealing with the compiler on your machine. If you enable Docker support, what's going to happen is your code, when you build it, it's going to create a container with all the SDK in the container. There's going to be a volume mount to your source code that you've stored on your machine, and it's going to compile your code in the container. That's the exact same process that will go on the build server. So you're not going to have the same case where it builds on your machine and not on the build server. It's going to do the same thing. It's the same base image that you're building upon. It's the same code. It should build exactly the same, right? So let's say if we go ahead and do that. I'll go ahead and create an MVC application. Yeah, like a couple minutes, right? Right. My home controller, I'll just go ahead and put a breakpoint right here. Just gonna fail on me again, I swear. Try to build it. You can do it. I believe in you. Oh well, okay. Let's go to break. This demo's not going to work, but the idea here, there's something weird with my box. It failed yesterday too. But it's very easy to set this up, run it on your own box. What this does is it brings up the containers in your own box, so they can start talking to each other. They'll be exposed on different ports on your box, and so you'll be able to talk to them on your box. You can then deploy them into a mini cube, which is kind of like a miniature Kubernetes environment in your box, so you can do more orchestration features on your box. But it's pretty well integrated into Visual Studio, right? Any more questions? No? Right, sorry, question right here. Does Service Fabric solve the monitoring issues? I do not believe so. For Service Fabric, I think you still have to depend upon application insights to do a lot of your monitoring. But Service Fabric itself will be able to give you some system metrics, but just service type communication, it won't give you that much detail, right? But just a system like, oh, I've got 5 machines and the average CPU is this much. It'll give you some information, but not much. But thank you for bringing that up, though. Thank you. I almost forgot about that. Application insights. Why aren't we using application insights? Was that your question? Okay. Okay. Next in the queue. So application insights. Actually, I'm talking about that in the next session, yeah. So yes. If I don't talk about it in the next session, remind me, but we're doing monitoring in this application, but we're using many other things besides application insights to do that. Your question? Thanks for the question. The question was around Service Fabric, ecosystem around that, and our direction around that. It's a little bit outside this topic. This project mainly focused on using ACS, but we can talk a little bit more about Service Fabric going forward a little bit later on. But just 10 seconds. Service Fabric was built by harvesting a lot of the functional bits that were used to create applications like SQL Azure, CosmoDB. Those are built on top of a flavor of Service Fabric. We figured, well, it was so successful for those, it might be successful for other people too. That's to some people have had great success with it, but that's outside of the scope of this project. But yeah, I'll let that team answer that. Actually, I'm on a project within Patterns and Practices to provide Service Fabric guidance, but we can talk about that on the break if you want. Okay. Okay. One question nobody asked me when we talked about the storage. What about SQL Server, SQL Azure? Why didn't you do that? Oh, too shy. Come on. I got 5 questions for you already. Right. So the question is, why not SQL? Why not relational databases? Come on, everybody uses relational, right? Well, did any of the services we have require transactional support? Deep querying? Fourth normal form? No. We're pretty okay with pretty denormalized data for what we're trying to do. We're trying to achieve high throughput. Locks, at some point we were okay with a little bit of data duplication for higher throughput. And that was our choice. And so different services chose what was appropriate for them, and nobody happened to choose SQL Azure. So that's just the case. We weren't pushing that, that was just the case. So the question is, for a very, very simple structure, are they really different? It may not be, but there's so many other things that you typically do with SQL Azure that may not make it so simple, right? Oftentimes the data you bring in, you want a fourth normal form. You want to have zero duplication of data. So it may lead you down a road that is typical for SQL, is not typical for just storing away documents. Exactly, right, exactly. I think Masashi talked a little bit about that. No, actually, we talked about that with the client. Yes, the ability to replicate and resiliency around SQL is very different, right? With something like CosmoDB, you can pick your other zones you want to have redundancy into. And if your primary zone were to fail, it automatically promotes one of the other zones to be a read-write replica. It happens very easily. There's some things that were just too easy to not take advantage of. All right. Good time to break. 10 minutes. All right. See you back in 10 minutes. Thank you.